Welcome to Eyewitness Virtual Reality EarthQuest. Ahead of you, in the Earth Gallery, is the Earth Builder, an interactive 3D tectonic plate challenge. Answer the Earth Builder questions correctly to rebuild the Earth's outer shell, then unlock the secrets of its past.
Magma rising up from deep in the Earth's crust erupts from a central crater as flows of lava and explosions of ash and pulverized rock. Most of the ash and lava from these eruptions collects near to the central crater, forming a distinctive cone-shaped volcano. After many hundreds of years, the eruptions build a tall, snow-capped stratovolcano. Earth tremors and bulging of the mountain show that large amounts of magma are ready to erupt. A small eruption releases the pressure within the volcano, allowing the magma inside to expand violently, triggering a massive eruption. A huge cloud of ash and pulverized rock blasts skyward, covering the landscape in layers of ash, and pyroclastic flows pour down the mountainside. The volcano collapses, forming a caldera. As magma forces its way toward the Earth's surface, the ground bulges and then splits into a small fissure. The fissure erupts a fountain of ash and larger pyroclasts into the air. These fall to the ground near to the fissure, building a steep-sided cinder cone. Ash from the eruption drifts over the nearby fields, blanketing crops and stripping the leaves from trees. A huge fissure, many kilometers long, splits open the Earth's surface. Vast amounts of very fluid lava pour out of the fissure, covering a wide area before hardening into the black volcanic rock, basalt. Over hundreds of years, the fissure repeatedly erupts more and more flows of lava, which accumulate on top of each other, forming a flood basalt plateau hundreds of kilometers across. On the seabed, fluid basalt lava erupts from an undersea vent. The lava flows away from the vent, following the contours of the seafloor and building a gently sloping shield volcano. After a few months, the volcano breaks the surface of the water, causing huge steam eruptions. The shield volcano continues to erupt lava and grows into an island.
In mountainous regions, an earthquake can shake loose snow, ice, and rock from a mountain slope, triggering an avalanche. The avalanche hurtles downhill at tremendous speed, collecting more snow and rocks and trees as it travels. A town that is unlucky enough to lie in the path of an avalanche may be swept away or buried in snow. At this earthquake in Iran, many people are trapped within the rubble of collapsed buildings. Rescue teams quickly move in to locate and dig out these people. One team uses trained dogs to sniff out survivors. Another team locates survivors by tapping out a message on the rubble and then listening for a reply from within the ruins. The shaking that accompanies a strong earthquake can totally destroy old or poorly built structures. Well-built structures, even high-rise buildings, are less likely to collapse, but their upper stories may sway from side to side. This swaying can be very dangerous, sending furniture crashing wildly about. Breaking glass and falling roof tiles are a hazard to those who are outside during an earthquake. During an earthquake, gas should be turned off as quickly as possible. Fire can take hold very quickly in a kitchen and soon spread to the rest of the house. In September 1923, a huge earthquake started fires in kitchens all over the city of Tokyo. 2/3 of the city burned to the ground, and nearly 100,000 people died in the resulting inferno.
Although this is only a medium-sized earthquake, it is shallow and close enough to cause some damage to the town. Indoors, furniture is moved around by the shaking of the seismic waves. Everyone feels the shaking, and some chimneys and poorly built structures are damaged. This medium-sized earthquake is too distant to cause much damage to the town. However, many people notice the vibrations of the seismic waves, and walls creak and dishes and windows rattle. There are thousands of earthquakes like this every year. This deep-focused, medium-sized earthquake is too far away from the town to cause any damage. People in high-rise buildings may notice a slight swaying, but no damage is done. Most people's experience of earthquakes is like this. This mighty earthquake destroys the town. The powerful shaking cracks roads and throws down sections of the bridge. It liquefies the ground, triggering landslides and ejecting mud and sand from the ground, which turns the river a muddy brown color. The tremors even seriously damage earthquake-resistant buildings, and other structures are shaken into rubble, and fires rage out of control in the wreckage. This powerful earthquake causes severe damage to the town. On poor ground, even well-built houses and office blocks slip from their foundations, and some sink into the ground as it liquefies. The shaking distracts drivers enough to cause automobile accidents, and landslips undermine roads. Fortunately, this powerful earthquake is too deep and distant to cause much damage. However, everyone notices the shaking, and most tall buildings sway significantly during the tremors. Most poorly built structures on loose sediments are extensively damaged by the earthquake.
An earthquake is a shaking of the ground caused by the sudden release of huge amounts of energy near to the Earth's surface. This often occurs when two tectonic plates move slowly past one another. The rocks at the plates' edges are put under enormous stress and start to bend, storing up elastic energy. Eventually, the stress overcomes the strength of the rocks, and they break, releasing their energy in the form of vibrations. It is these vibrations, called seismic waves, that cause the shaking in an earthquake.
At Mauna Loa volcano in Hawaii, a huge fissure opens in the ground, erupting spectacular fountains of glowing lava. At Kilauea, also in Hawaii, lava bubbles more gently to the Earth's surface, filling a crater with a huge lake of lava. Its surface blackens as the lava cools. From time to time, the lake overflows, and the lava pours away in streams of glowing molten rock. White Island is an active volcano in New Zealand. Most of the time, the volcano gently releases clouds of white steam and sulfurous gases. Sometimes, however, explosions occur within the crater. Gray and brown clouds of hot ash billow from the explosions. Rock and fresh magma is blasted into tiny fragments and scattered from the growing eruption cloud. Geysers are hot springs that erupt columns of boiling water. Groundwater, heated by magma beneath the Earth's surface, boils and rises to the surface where it is blasted forth as a geyser. Mud pools form at volcanic vents called fumaroles, which only erupt gases. The gases are acidic and quickly attack and alter the rocks around them, turning the vent into a pool of bubbling mud. Pillow lava forms when hot molten lava comes into contact with cold seawater. The surface of the lava cools and hardens into a bulbous crust, but the inside remains liquid. Each pillow spawns another as its crust cracks, and a new bulbous lobe oozes forward. Pillow lava is the most abundant volcanic rock on Earth.
This earthquake in California originates at a shallow depth. At the monitoring station, represented by the blue dot, the surface waves, shown in yellow, leave a short but powerful trace on the seismogram. As the surface waves travel further from their origin, however, they start to spread out. By the time they reach the monitoring station on the Cook Islands, the surface waves shake the seismograph for a much longer time. The primary and secondary waves from this earthquake in California travel through the interior of the Earth. As they encounter the different layers of rock within the Earth, their speeds and paths are deflected. The surface waves, shown in yellow, stay concentrated near the Earth's surface. These waves register the most clearly on the seismograms. The monitoring station in Tasmania, represented by the blue dot, is the closest to this earthquake in New Zealand and is the first station to detect the seismic waves. Some minutes later, the seismic waves reach the island of Guam in the Pacific Ocean, and shortly after that, the Hawaiian Islands. The slowest moving seismic waves are the powerful surface waves, shown in yellow. These take more than 30 minutes to reach the monitoring stations at Guam and Hawaii. The primary waves, shown in red, and secondary waves, shown in blue, from this earthquake in New Zealand, pass through the inside of the Earth. The temperature and pressure increases the deeper the waves travel into the Earth, and their paths start to bend slightly. When they penetrate a different layer within the Earth, the course of the seismic waves is greatly altered, and some of the waves are even reflected back, away from this layer. The seismic waves from this earthquake in the Kuril Islands travel swiftly around the globe. Within a few minutes, the fastest seismic waves reach the monitoring station at Hawaii, indicated by the blue dot, where their faint trace is recorded on a seismogram. It takes a few more minutes for the surface waves, shown in yellow, to reach Hawaii. Their powerful impact shows up clearly as a strong pulse on the seismogram, although they wouldn't be felt by the island's inhabitants. The patterns left by the different types of seismic waves on the seismograms can be seen clearly in this animation. The initial impact of the red primary waves shows as a small pulse, while the blue secondary waves leave a slightly larger trace on the seismogram. This is a shallow earthquake, and most of its energy is contained within its train of surface waves. The trace left by the surface waves is much larger than that of the other waves. Seismic waves spread out from this shallow earthquake in Japan. Within a few minutes, the waves are detected at the monitoring station in Taiwan, represented by the flashing blue dot, and soon after this, at the station on the island of Guam. Most of the earthquake's energy is contained in its surface waves, shown in yellow. These register as the largest peaks and troughs on the seismograms. This cross-section shows how the three different types of seismic waves travel through the Earth. The primary waves, shown in red, pass through all parts of the Earth, although their speed and direction is distorted as they pass from one layer to the next. The secondary waves, shown in blue, only travel through the outer sections, the crust and mantle. Most of the energy of the surface waves, shown in yellow, is confined to the crust, the Earth's thin outermost layer. Most of the energy of this earthquake in Georgia is concentrated in its surface waves. As the primary and secondary waves reach the monitoring station in Japan, shown as the blue dot, their impact hardly registers on the seismogram. The same is true when they reach the stations in California and Oregon, which are on the other side of the globe. However, the surface waves, shown in yellow, register very clearly on the seismograms for all three stations. The seismic waves from this shallow earthquake in Georgia form a complex pattern as they move through the inside of the Earth. The paths of the waves are reflected and refracted as they travel deeper into the Earth, much like light passing through cut glass. This is because the speed and direction of seismic waves are altered when they encounter the different layers within the Earth. This exceptionally powerful earthquake in Bolivia originates at a very great depth. Due to its depth, it does not generate any surface waves. Its primary and secondary waves, shown in red and blue, register very clearly on seismograms at monitoring stations around the world. This very powerful earthquake in Bolivia originates more than 600 kilometers beneath the Earth's surface. Primary waves, shown in red, and secondary waves, shown in blue, spread out from the earthquake, and their shaking is felt over a very wide area. No surface waves are generated, however, due to the depth of the earthquake.
This machine is drilling blast holes. The next step is to charge up by loading explosives into the holes. Then, once people and machinery have been cleared from the blasting area, the explosives are detonated. Note how the explosives are timed to go off in sequence, which lessens the ground and air shock produced by the blast. When the dust has cleared, The exploded rock will be loaded into trucks. This open-pit mine in northwest Australia produces over 20 million tons of iron ore each year. Here, a power shovel is loading blasted rock into a rear dump truck. On the level above the machinery, you can see where blast holes have been drilled. The truck to the left sprays water onto the roads to settle the dust and to keep the roads in good condition. At 800 meters deep and 4 kilometers across, the Bingham Canyon open pit mine in Utah, in the United States, is one of the largest man-made holes on Earth. It can even be seen from the moon. This aerial shot shows how the mine reaches deep into the Earth as it follows the ore body downward. The Bingham Canyon mine has been called the richest hole on Earth because it produces valuable metals such as copper, gold, silver, and molybdenum. In this platinum mine, the miners are transported underground by chairlift. Here, blast holes are being drilled and charged with explosives that break up the ore. The blasted ore is scooped up by loaders, dumped into trains, and transported to collection points. The ore is then crushed and taken by conveyor belt to skips that are hoisted to the surface.
"5 billion years ago, the Earth did not exist. The solar system was just a cloud of dust and gas on the edge of a huge galaxy. As this cloud contracted over time, much of its gas and heat became concentrated at the center. A flattened disk of dust rotated around the mass of dense gas. Dust collided and stuck together to form rocky chunks. The large rock fragments grew fastest as they swept up the dust in their path. The infant sun suddenly flared up, creating a solar wind that swept away the gas and dust. The bodies that remained were the planets, moons, and asteroids of the solar system. Secrets of the Earth's past are contained in its rocks. Exposed layers of rock help geologists piece together the history of the Earth. The sediments that make up sedimentary rock accumulate in layers. As each layer is deposited, it buries an earlier layer. Thus, the deepest layer in a stack is the oldest rock. The overlying layers consist of younger rock. To find out a rock's age, geologists study any fossils it contains. For example, this type of ammonite was common about 200 million years ago, so the rock must have formed at that time. In this way, fossils give vital information about the Earth's past. The Earth's outer shell, which includes the crust and upper mantle, is made up of moving sections called plates. There are several large plates and many small plates. The plates are continuously being created and destroyed as they move around. Their movement changes the surface of the Earth. The Pacific Plate, on which Hawaii lies, is carrying the island about 8 centimeters closer to Japan each year. At the same time, the plate that carries North America is moving about 2 centimeters away from Europe every year. The boundaries between the plates are where most volcanoes and earthquakes occur, showing the immense power of these slowly shifting plates. Like many other bodies in the solar system, the Earth is made up of distinct layers. The 3 main layers, the crust, the mantle, and the core, Each contained different kinds of minerals. These layers developed in the early stages of the Earth's history. It is thought that when the Earth formed, it contained a uniform mixture of rocks and metals throughout, symbolized here by spheres. The planet was so hot that the materials melted. Slowly the liquid began to separate. First, the heaviest material, molten iron, sank to form the core. Molten silicate rock crystallized, forming the mantle. Later, some of the mantle melted, forming liquids that rose to the surface and solidified to become the crust, a process that is still occurring today. $4.6 billion years ago, the Earth was a mass of red-hot molten rock. As the planet cooled over millions of years, a solid crust formed. Hot gases bubbled up from below the surface, erupting from volcanoes to form a thick atmosphere. At the same time, meteorites were smashing into the surface, making thousands of craters. Before the Earth was 1 billion years old, it had cooled enough for water vapor in the atmosphere to condense as liquid water. This fell as rain for millions of years, creating the Earth's oceans. The planet was beginning to resemble the world we know today.
The surface of Mars is scarred by craters, volcanoes, and canyons. This computer-generated journey begins at the eastern entrance to a huge system of canyons called Valles Marineris, which is 4 times deeper and 10 times longer than the Grand Canyon. Ahead is a row of 3 volcanoes. The first, Arsia Mons, is topped by a crater more than 100 kilometers wide. These volcanoes are far larger than any on Earth. From Earth, Mars appears reddish because large areas of its surface, especially its broad sweeping plains, are covered in red iron oxide dust, commonly known as rust.
Constant battering by waves gives many coastlines a jagged, irregular shape. A coast can consist of many different types of rock, some of which are more resistant to erosion than others. Bays are sculpted from softer rock as waves curve around a headland. Pillars of rock that rise out of the sea are remnants of a past shoreline before the coastline moved inland. Volcanic islands build up from the sea floor as eruptions of lava cool and solidify. In tropical waters, a coral reef can form around the shoreline of a volcanic island. If the volcano stops erupting, the seafloor underneath the volcano, once buoyed up by the heat of the molten rock, sinks when no more molten rock is produced. However, the reef continues to grow, leaving a lagoon between the sinking volcano and the reef. Some of the world's largest mountain ranges are made from rock that has been folded between 2 of the Earth's plates as they come together. As the mountains are lifted upward by forces underneath the surface of the Earth, rain, ice, and wind erode the rock, shaping it into peaks. High, jagged peaks are the mark of young mountains. As a mountain range grows older, the peaks will be worn into gentle slopes. The motion of the Earth's plates can cause 2 continents to move toward each other. Where the 2 plates meet, the dense oceanic plate subducts, or goes under, the continental plate. The ocean begins to close up, and the continents move closer together. Seafloor sediments are too light to be subducted, so they fold and become part of the forming mountain belt. When the ocean is totally closed, the two continents collide, lifting the area upward. The whole region folds and fractures. At the same time, wind, rain, and ice carve peaks out of the folded rock of the mountain range. Many high mountain valleys bear evidence that glaciers were once present in a colder period. Typical signs that large rivers of ice have sculpted the land include broad U-shaped valleys surrounded by jagged triangular peaks. As glaciers move downhill, pulled by gravity, they carve out valleys and carry away rocks they loosen. These are deposited along the valley floor when the ice melts. Running water, wind, and snow slowly but continuously alter landscapes through erosion. In this landscape, rock beds have been folded by the movement of the Earth's plates. Over time, erosion is wearing down the uplifted areas and filling the hollows with sediment. Erosion has cut deepest into the soft layers of exposed rock, creating valleys. The harder, more resistant rock layers form a series of parallel ridges. A deep, narrow river valley, called a canyon, forms when a river cuts out a channel faster than weathering and erosion can wear away the sides. Canyons are often found in dry regions where the lack of rain means that weathering takes place at a very slow rate. As a river carves a canyon, it exposes layers of rock that have been laid down over millions of years. A desert is an area where rainfall is very rare. These dry landscapes have sparse vegetation and consist mainly of bare rock, sand, or salt flats. However, when the rain comes, it is torrential, flooding through gullies and washing away loose dirt that is unprotected by vegetation. Tables of rock, called mesas, rise up steeply from the surrounding land. A rift valley forms as two of the Earth's plates move apart, causing the crust to crack and a block of land to drop down. Two parallel faults make up the walls of the valley, while the section that is dropped down becomes the valley floor. The movement of the plates under the area means that rift valleys are often the site of volcanoes and earthquakes. Where hot rock wells up from deep within the Earth, the crust warps upward. This causes the crust to thin and crack, and molten rock to erupt at the surface. As the plates move away from the region of upwelling, a broken section of crust drops down to form a valley. The crust continues to thin and crack as the plates move apart, causing the rift valley to widen as sections fault and drop down. In this way, a rift valley gradually forms. Its stepped sides become smoothed over time by erosion. Pangea was the supercontinent that was made up of all the world's land joined together. It existed at the beginning of the Triassic period, 250 million years ago. The northern part of this great continent is known as Laurasia, and the southern part as Gondwana. The vast continental interior was dry desert because the storms coming off the oceans dropped all their rain near the coastlines, with little moisture reaching the interior. Pangea slowly moved northward, carried by the plates underneath the Earth's surface. It started to split as the beginnings of the Atlantic Ocean opened up between North America, Europe, and Africa. Laurasia and Gondwana were the two main areas of land at the beginning of the Jurassic period, 200 million years ago. In eastern Gondwana, the outlines of India, Australia, and Antarctica were visible. Western Gondwana comprised Africa and South America. A rift opened up between Laurasia and Gondwana as the plates underneath the area moved in opposite directions. The ocean between the two landmasses widened, causing them to separate. On the west coast, a mountain chain was forced up as two plates crunched together. Around the world, rising sea levels caused the oceans to flood into low-lying areas. At the beginning of the Cretaceous period, 140 million years ago, the outlines of Africa, India, Australia, parts of Asia, Antarctica, South America, North America, and Europe could be seen clearly. Southeast Asia moved north and merged with the large landmass that was Laurasia. Africa, India, and Australia broke away from Antarctica. Meanwhile, the very active spreading ridge on the seafloor of the forming Atlantic Ocean widened the ocean, pushing apart Africa and South America, and Europe and North America. India and Africa were carried north by plate movement. Rifts began to appear in East Africa that would eventually open up a new ocean. 20 million years ago, India collided with Asia. The impact of the collision pushed up the mountain range known as the Himalaya. Gradually, the land masses moved into their present positions.